Okay, so we will be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, so the next topic that we're going to cover has to do with steady state and steady state errors. You guys already did a little bit of research regarding this, where I asked you to watch a couple of videos and try to get your heads around the concepts of final value, steady state, and steady state error. So this is the next topic that we're going to be addressing. So you've already got the background of this. So how do we define the steady state error? The steady state error is going to be referenced with regards to the final value that a system's response is going to have when time tends to be infinite for the situation of a stable system. Remember that when we have a stable system, it's a system where we have a transient and then that transient ends. And after the transient is what we consider to be called the steady state of the system. And so when we apply a certain test input and we measure or compare the response of the system when time tends to be infinite, there is going to be a certain value associated to that. And that value in comparison to the value we want the system to get to, that difference that exists when time tends to be infinite is what we call the steady state error. Now, remember that there are certain types of test inputs that we're going to usually be applying to a system. And so for the purpose of this topic, we're going to be talking about three types of test inputs. Why these three? Because they can literally be or directly be associated with some physical variables. So the first type of input is the step input, which is basically a constant. Now, let's imagine that we're talking about a mechanical system of movement, okay? So what would the step input represent? The step input would represent a position, a current position and a constant position. So the step represents position, okay? And we already know the time function and the corresponding Laplace function. But the step is going to represent a position, okay? And remember that I even asked about this in the exam. Remember, if anybody has any questions, please just unmute your microphones and go ahead. So the step is going to represent a position. Now, the next type of test input that we're going to talk about is the ramp. What would a ramp represent? A ramp is going to represent a position that is changing at a constant rate. Or, said in, if we express this in other terms, it's going to represent a velocity, okay? So again, the ramp is representing a position that is changing with a constant rate. And what do we call that? We call that velocity. Meaning the ramp is going to represent, I'm trying to follow something that's moving. And I'm trying to continuously be able to reach that or be able to follow that object that is in movement. And lastly, the parabola. What is the parabola input going to represent? Well, the parabola input is going to represent an input that is moving at a certain rate and there is an acceleration, meaning that the velocity is changing constantly throughout time. So the object is not only moving, it's moving at an accelerated rate, okay? Now let's see what we're talking about. Let's assume that we've got our antenna system. We've got our antenna system. And let's assume that the antenna system is going to be used for different purposes. So the first purpose that we've talked about is making the antenna go to a certain position. And I think, again, that this was a question in the exam. If I make the antenna go to 30 degrees, what type of input am I talking about? Well, I'm talking about a step input because I'm telling the antenna to go to a certain position, meaning I'm located here and then there's an object that's over there. And so the antenna is going to move to point at that object. it is a constant position that I'm trying to reach. The set point is a constant position. Now, I believe you should agree that there's different, depending on the characteristics of the system and the gains that we provide, is how the antenna is going to reach that position. And in the end, if there's going to be a certain error when we reach that position, which is the difference between the position and the actual the position I want and the actual position of the antenna. So, for example, if I told the antenna to go to 30 degrees, but then the antenna in the end ends up in 30.1, well, there's a difference there of 0.1. There's an error. So that's the positioning type of input. But now let's imagine that instead of telling the antenna to go to a certain position, or rather, I told the antenna to go to 30 degrees because there was an object here, and then the object starts moving. The object starts moving through space at a constant position, and I want the antenna to track it. So I want the antenna to follow it. So now the object is moving at a constant position, at a constant velocity, I'm sorry, and the antenna should be moving to follow it. Can somebody tell me what's going to happen if the antenna is too slow? Daniel, go ahead, shoot. Daniel, go ahead. We can't hear you. Yes, Daniel, go ahead. We still can't hear you. I could hear you before when we did the attendance, but we can't hear you. While Daniel fixes his mic, anybody else? What's going to happen if the object is moving at a constant speed and I can't match that speed? What's going to happen? Adrian.
You're going to lose the track of the object.
I'm going to lose track of the object. Why?
Because it's going to be slower than the object.
Yeah, the object is going to start moving, and I'm going to start following it. But if I'm too slow, the object is going to continue to move, and there's going to be a difference between there's going to be a difference there, and I'm not going to be able to track it correctly. Now let's assume that the object is not only moving, but it's moving at an accelerated speed, meaning that it starts off slow and then it starts moving faster. I can't be moving at a constant velocity. I need to be moving at an accelerated velocity to be able to reach it. And the same thing is going to happen with the other situation. If I can't accelerate quickly, then I'm going to lose the object. Okay? Imagine that you are driving on the road. You're driving, and this is you, and then you've got another car in front of you. And you want to maintain this distance constant or as close as possible. That means that your two velocities should be matched. But if the car in front starts to accelerate and you don't accelerate, then that distance is going to grow. Now, if the car in front of you starts to accelerate and you start to accelerate also, if you don't accelerate enough, also the distance is going to grow. But if you accelerate too quickly, you're going to hit it. Okay? That's kind of what we're talking about here with the different types of inputs that represent position, velocity, and acceleration. Now, for each of these cases, we want to study, assuming that the system is stable, we want to study or we want to understand in the end, how far apart are we going to be from the desired value, depending on the type of input. And this is going to depend on the characteristics of the system. And in the end, these characteristics of the system are going to be given by its transfer function. So let's analyze this. Let's evaluate the steady state response to this system for three situations. 5u of t, and this one here, this is the step. 5tu of t, and this is the ramp. And 5t squared u of t, this is the parabola. So it's position, velocity, and acceleration. We want to see how the system behaves for each of those three cases and see the steady state response. Okay. Okay, so I'm going to switch over to MATLAB. So we can do this. Okay. So if I do this, you're seeing MATLAB right now?
Yes.
Yes.
Okay, and if I switch over, you see the PowerPoint, right?
Yeah.
Good. We're good then. Okay, so we're gonna implement this system in MATLAB, and we're gonna analyze the steady state. Now, what I'm gonna do now over here in MATLAB, I'm gonna do a CLC. I'm gonna first define the system. So the transfer function that we've got here in the, oops, the transfer function that we've got here in the middle, we're going to be calling this g of s. That's going to be g of s, and that's the first thing that we're going to define. So I'm going to say sys g, I'm going to call it, is going to be I need to change the language here or else MATLAB doesn't cooperate. Okay, so sys g is going to be the transfer function of, we've got 120 times s plus 2. So it's going to be I'm going to say this is equal to 120 plus the first polynomial here is s plus 2, which is 1 and 2. Remember, you can follow along with this as you want, as you wish. And in the bottom, we've got an s plus 3 and an s plus 4. So I'm going to do the convolution of s plus 3, which is 1, 3, comma, s plus 4, which is 1, 4. And that's going to be the forward transfer function that we've got there. Okay. And now I'm going to do the whole system, because remember that we're going to analyze the whole system. So I need the whole transfer function. And to do that, I'm going to call this sys 7.2. I'm going to call it example 7.2. This is going to be a feedback of sys g comma 1. The feedback that we have here is unitary feedback in h of s, so it's going to be 1. And we've got that. Okay. Now, remember that we had used, for example, to do the step, we know we can use the step function. Okay. Now, remember that the step function by default, applies a unit step to the function. Okay. But the function here is 5 units in each case. So how do we do that if we're going to be using the step function? We have to remember that in the end, what we have is C of S, which is the output, divided by R of S as the transfer function. And so if in the denominator, and this is equal to G of S divided by 1 plus G of S. Okay. Now, if R of S is equal to 5 times the unit step, then if we substitute this here, we're actually going to have C of S divided by 5 times U of S equals the transfer function, which is g of s divided by 1 plus g of s. But if you notice, I can send this 5, I can eliminate it from here, and I can just put it here. And it would be equivalent. So actually, when I'm using the step function and I'm applying an input that isn't unitary, the only thing I need to do is multiply by that factor the transfer function. And so in this case, going back over here, I can just say 5 times sys 72, and that's going to give me the graph for the response. Just wait for it to do that. There we go. And here we have the graph for the response. And notice that if we go over here to we can actually click here steady state, which is going to be the last value. If we click here, we're going to see that the final value is 4.76. That means that I'm telling this system to go to 5, which is the reference, and it's never reaching 5. The maximum value it reaches is 4.76. Okay, that means that I've got an error there, a slight error of 0.24. Okay, now is that relevant or not? Is that acceptable or not? Well, that's going to depend on the system characteristics. But the thing here is that I've got an error. Now, as we're going to see, there's ways in which we can eliminate this error and have the final value be exactly the one we want. Okay, and we're going to see that in a bit. Okay, now I want to show you another way to do exactly what we did here, but instead of using the step function. Why? Because if we use the step function is particularly to apply a unit step to a system. However, here we're going to have to apply a ramp and a parabola. And there's actually not a MATLAB function for a ramp and a parabola. There is a ramp function in Simulink, but not in MATLAB. And so how can we generate a system response to any type of input? Well, there's a mathematical expression in the control systems toolbox that we can use for that. And I'm going to call up help a function called LSIM. And you can do the help also, and you can search with F1. Now, what does LSIM do? LSIM simulates the time response of dynamic system to an arbitrary input. What does this mean? We can define any sort of input we want and provide it to a certain system, and LSIM is going to graph it. Now, how does LSIM work? LSIM receives the system that we're talking about and receives 2 vectors, which is U and T, which represent the which are going to represent the function that we're trying to apply to the system. And so what we're going to do here is that I'm going to define a vector T that's going to go from 0 to, actually I already have it defined here. I'm going to define a vector T that's going to go from 0 in increments of 0.001. Let me do a clear screen here. Start up. I cleared everything. Well, doesn't matter. I'm going to first define a vector T, which is going to go from 0 in increments of 0.001 up to 1. We can define whatever limits we want. And then I'm going to define a vector U that is going to be a constant. Now, how do I define a constant? There is a function here that I can use that's called repmat. What does the function repmat, this one here in MATLAB, do? the function repmat is going to fill in a matrix of n times m with the value that I wanted to fill up. So in this case, I'm saying that I want a vector u that's going to be filled up with 5s because it's a constant. It's going to have 1 row and 1001 columns to be congruent with the vector t. I'm not making an echo in the screen because it's going to show all of the values. If I were to do just plot t comma u, just what do I get if I do a plot t comma u? Well, I get a 5, a constant 5. Okay. And so I can define any function that I want. I'm gonna have to define my system again because I did a CLC, so I erased everything that I did. So I'm gonna do that. I'm gonna do that again. I'm gonna do this first. Then I'm going to do this. Okay. And now instead of calling the step function, I'm going to call the LSIM function. The system is going to be sys72, which is the one I have, and I'm going to give it u and t, meaning that's going to be the two vectors of the there's going to be the two vectors of the input I'm providing the system. And let's see what we get there. We get a very similar graph. Why does it look different? In the case of the step, I think it graphed it up to 0.24. It was graphing up to this point. I specifically asked to graph until 1. Okay. And if we notice here, if we go to the last or to the final value, we get a 4.77, which is the 4.76 rounded that we had originally. Okay. So this is just another way of doing exactly the same, the same thing. Now let's give it a ramp function. To give it a ramp function, I've already defined my vector t. And so what now I'm going to do is that I'm going to say that u equals t. I'm sorry, u equals 5 times t, because remember that the function we're giving it is 5t. And I'm going to plot that just so you see what that is. Plot t comma u. And what we should get is a line that has a slope of 5. Okay. There's a relationship of 1 to 5. That would be the input that I'm providing. And we're going to do a LSIM. And notice what we have here. This, in the first case, the previous case, was that we told, let's imagine that this is the antenna, all right? We're telling it to go to 5, and we saw that it tried to reach 5, but it kind of reached 5, it reached 4.77. Now it's different. We're not telling it to go to 5, we're telling it to follow an object that's moving at 5, let's say, meters per second. And so the gray line is the reference or the input. The blue line is what the system is trying to do. So what do we notice here? The system is trying to follow the object, but what do we notice here with regards to the difference between the movement of the object and, in this case, the movement of, let's assume that this is the antenna. What are we noticing there? Daniel, go ahead.
It's starting to separate, like when the time increases, the gap makes like wider.
Gets wider, correct. That means that the object is moving at a certain speed and I'm trying to react, but in the end, I'm slower. And so what's going to happen when time goes forward, there's going to start being a gap. And ultimately, that gap is going to grow and the error is going to grow. And that's something I don't want. Again, we're going to see how we can try to eliminate this gap. But for now, this is the way the system is responding. Now let's provide it an input as a parabola, meaning now we're going to have a system that has we're going to have a system that has an input. Go to the command window. Has an input that now has a constant acceleration. So first we're going to define our vector t. Now, let's see how many of you are awake. How would I define, if it's going to be a parabola, how would I define u in this case? According a parabola with a constant of 5, how would I define u in this case? Okay. If somebody doesn't answer, excellent, that's great. Adrian, go ahead.
I'm not sure, but I think 5 divided by 2 multiplied by t squared.
5 divided by 2 multiplied by, why divided by 2?
Because I think the parabola function is the medium for the t squared.
Okay, remember that we're not doing any sort of derivative or integral or anything like that. We literally want to do this. So you're on the right track, Adrian. So we literally want to do this here. So I'll ask again, how would we implement this here in MATLAB? Let's see, Daniel.
Oh no, I was just gonna say that multiply it by the variable to the square, but I don't think that's the correct answer.
Yeah, but literally tell me how it would be. Anybody, literally tell me how it would be in MATLAB. How would I write this code in MATLAB? This is basic MATLAB, by the way. What I'm asking. How would I write it here in MATLAB? Okay, we're going to do one of these techniques. If nobody gives me an answer or an idea or an approach to an answer in 2 minutes, then I'm going to deduct 5 points from the next exam to everybody in the classroom.
As 5t squared, Professor?
Yes, Luis, but how do I write that in MATLAB?
I think it's POW, like PO or exp. I don't remember how to do the squaring, or maybe with the little hat, like the upwards arrow.
Okay. Yes, I'm gonna literally give you guys a minute to maybe even Google it. I've got a proposal. So your proposal here, Luis and Adrian, we could do something like this, and I'm just going to write it down, which is the little thing here. Why can't we use that one? We're not talking about constants. We're talking about a matrix or a vector. Remember that vectors and matrices here are the same. So we can't use the little tilde thing. But you were on the right track, Luis. There has to be a function that I can use in MATLAB to elevate something, a vector or anything, to a power. Remember that MATLAB functions are polymorphic. So again, there's 1 minute for you guys to find that.
Teacher, Professor, is the dot with the thingy that, isn't it? Like when you use the vector, that means that you multiply like each one.
So let's see if this one could work.
Before the symbol.
Yep, I'll put it here in the T. I don't want to, I'm going to put the semicolon there because I don't want to repeat it through the whole screen. So that seemed to have worked. Good job. You guys didn't get points deducted. I'm going to be doing that from now on because only a couple of people are participating. So I just want to know if the rest of you are there. And the other thing is that I know you guys are smart. And if I asked you to Google anything else, I know you would. So that's good job. That's a solution, and it even says there. There's another way of doing this also. There's a function called power, which would be t, 2. that I could also use. Okay, so
I said
either of
that,
the-
Professor, and you said I was wrong.
no, I didn't say you, you said POW. I never said anybody was wrong. I said, I was asking to Google it. In this case, it's power. I'm not sure if POW is also one. I know that POW, I think, is one that you can use in Excel. POW isn't one, but power is. POW2 is another one. Okay. So this could be another alternative. Either of those could work. Okay. So now we've got U and T. We can run the LSIM again to run the function here. And what's happening here? Very similar to the one we previously saw with the velocity. Notice this. If I ask, this is the same system under three situations. If I ask this system, the way it's configured, if I asked it to go to a certain position, there was an error, right? That was the first case. Then I asked the same system to track something that was moving, and there was an error, slight error also, that increased. And then I asked the same system to try to track something that's constantly accelerating. So if the system cannot go to a specific position, then it probably won't be able to go to, or there's going to be a constant error trying to go to a position. There's probably going to be an error trying to track something that has a constant velocity. And if the system can't track something that has a constant velocity, it's probably going to have trouble tracking something that is accelerating. And we can see this here in the response. In the acceleration, the gray line is the reference. The object is constantly accelerating, and the blue is in this case, let's assume again that it's the antenna. The blue is the response. It's not being able to accelerate quickly. So again, the object is going to be going further away. So the takeaway that we have from this system in particular, the way this system is configured, is that this system, the way it's configured, it's not going to be very good for inputs that have velocity or acceleration. Okay, we might need to change something in this system to try to make it react better to those situations. But currently, the way it is, it's not doing a very good job. Okay, I hear in the PowerPoint in the next slides. I'm just showing these same results that we saw there in MATLAB. Okay, and you're going to have them there. The only thing that's on the slides is the code, but you're going to have the recording. Now I'm going to give you a few minutes to try to process and do this one. You can have your MATLABs open. I'm going to give you a couple of minutes to try to work on this one, and you can ask questions individually, and we'll be back to see what we find here. What's the main difference? Let's see how your mathematical eye is. The two systems are different. The two systems are different. Okay, the two systems are different. This one and this one, they're definitely mathematically different, and therefore they're going to behave differently. But can somebody tell me or identify? And I'm going to put them side by side. Can somebody just off the top of your heads, comparing these two, what do you notice between one and the other? Just things that are different between each of them. That again, we might want to take note mentally when we go and analyze them and analyze their behavior. So let's see, Ariane, go ahead.
What I see different is the order of the system.
Correct. That's a very good observation. The order of the system is the second system that we're analyzing, the 7.3, is of a higher order. That's a good observation. Anything Thank you, Ariane. Anything else? I think Angelica also you raised your hand. Was it
I
that
was-
thing?
Yeah, I was gonna tell.
Well, let me stay with you, Angelica, because you raised your hand. So it's or like Ariane mentioned, and you identified also, I think they have the second system, the 7.3, this one here, has a higher order. Oops. Moment, I'm gonna go forward. Has a higher order, this one here.
Yes.
But also, what else do you notice between, let's look at the denominator. Is it just the order that's different?
Well, it's the same denominator, but the order of the second one is not from the first one is higher, but it's the same one.
It's the same, but what's the main difference between one and the other besides the order if we look at the if we look at the factors? This one is the same as this one. This one is the same as this one. And what's different?
Well, yes,
The S, right?
but that is what makes it a higher order, right?
Yes, but let's look at what type of higher order. If I multiply these two, Angelica, am I going to get a constant in the resulting polynomial? And am I going to get a constant value?
Yes.
Yes, right?
Mhm.
Because this is equal to S squared times 7S times 12, right, Angelica?
Yeah, and because of the S on the first one, we won't have a constant.
We won't have it, right? We're going to have S3 plus 7S squared plus 12S, and we're not going to have a constant value here. Actually, we're going to notice that that's going to affect the behavior of the system with regards to the different inputs, okay? So good observations there. Thank you, Ariane. Thank you, Angelica. Okay, I'm going to give you a couple of minutes to try to do this one in MATLAB, the same things, this exactly the same things we did, which is basically to find the steady state response for those three situations. I'm going to give you a couple of minutes to try to do that, and then we'll start doing it here. Okay, let's see what we can do here. Now, the first thing we need to do, and I'm going to switch over to over here to Blackboard, is that we're going to define this. We'll do that before we go to break. We're going to define this transfer function. Let me just check if I'm doing, there we go. So again, if I do this, you can see PowerPoint and MATLAB, correct?
Yes.
Okay, so we're going to define this. I'm going to call this sysg is going to be equal to 100 times TF of, there's going to be 2 there. There's going to be the convolution of 1, 2, comma, 1 and 6. And on the denominator, we're going to have the convolution of the convolution of 1, 0 multiplied by the convolution of 1, 3, and 1, 4. Okay, let's see, is that correct? 100 times the convolution of 1, 2, and 1, 6. That's going to give me the numerator. And then the convolution of 1, 0 times the convolution of 1, 3, and 1, 4. Okay, well, that's going to be sysg. Okay. And we're going to do the sys, I'm going to call it 7.3. It's going to be the feedback of sysg, comma 1. And that's going to give us the complete transfer function. And we're going to analyze how the system behaves for each of the situations. So the first thing I'm going to do is that, again, I'm going to define a vector t. I'm going to define this. The first one is going to be the constant, the 5 constant. So again, I'm going to do the rep mat 5, 1 to 101. And I'm going to do an LSIM of system 7.3 with those 2 values. And what we're going to get is this. We've got a system that's seems to have a bit of an overshoot. And what do we notice here in the final value of this system? What do you notice with the final value? We're trying to get to 5, and what is the final value in comparison to the previous one?
5.
The final value is 5, and we're trying to reach 5. So in this case, the difference to the other one, if you notice, in the previous one, we wanted to reach 5, and the final value was 4.77. Okay, and so. Okay, Misael, why don't you mute your microphone so I don't have to?
Sorry.
Thank you. Don't worry about it. There's going to be a difference there, or in the previous one, rather, we had a difference. We wanted to reach 5, and the final value was 4.77. Here, we want to reach 5, and we're reaching 5. The error is 0. So that's good. So, curiously enough, if I modify the denominator and add an S to it somehow, I'm actually improving the steady state response of the system to a step input, okay? Now, the next is to see how the system behaves to a ramp input. Okay, so we saw the response for the system for the step input, the 5-step input. So now we see that this system is able to reach a constant final value for a step input. Now let's see how the system behaves to a ramp input. And so again, we've already defined T, so now we just need to define U. And, oh, I'm sorry, that was the parabola. We define U as 5 times T. Now we do the sim. What do you notice here in this response? Apparently, from what we're seeing here, what do we notice in this response that's different from the response of the other system for the same ramp input? Can somebody notice something here? I'm just going to put it here on the screen.
It is not 5.
Look at this one. This is how the other system responded to a ramp, meaning an object that was constantly moving. And now this is how this system is responding. What do you guys notice? Let's see, Marco.
They seem to be in parallel.
And what does that mean? Correct, Marco? But what does that mean, Marco?
That the error is constant.
That the error is constant, correct. And good. And what does it mean with regards to the movement of the antenna? There's an object that's constantly moving, and the antenna is trying to track it. What does this response mean? It's correct what you mentioned. The two lines are parallel, and the error seems to be constant, because if I go along this line, okay, if I go along this line, the error, it's kind of following the other line. It's not getting larger. So what does this mean with regards to the antenna and the object? What do you think?
It's like it's effaced.
Did you say that again? I didn't hear the last part.
Like in a different phase in movement in relation with the desired movement.
What do you mean by a different phase? Don't start throwing around science fiction terms just to, what do you mean by a different phase?
I don't know how to explain it.
Well, give it a try. And if you need to make movements or try to explain with objects, please give it a try. Because I think you do understand what's happening, but I need you guys to be able to explain these things. So you gave it a very good, you're giving it a very good try, Marco. Just try to explain it because you do have the idea. Okay, I don't want this to be academic bullying, so that's fine, Marco. Let's see if somebody can help you out. Can somebody explain what's going on? What Marco said is correct. You're looking at the graphs. The gray line is the object and it's moving at a constant velocity. The blue line is the antenna that's trying to respond. And thank you very much for raising your hand, Daniel. But I'm actually going to give you extra points in the exam because you're the only person that's participating in every session and in all of the questions. And I recognize that because you always participate. You're not sure if the answer is going to be correct or not, but you always participate. And I recognize and I acknowledge that. But we've got a bunch of other, this is a smart group. We've got a bunch of smart people here and I want to hear them. Let's see, Adrian. And Marco, well, Marco wanted to give it another try. I want to give it, Marco, if you want to give it another try, Marco, you've got preference. Go ahead.
The antenna is following the object in correct way. I mean, it's doing the job.
Yes, correct, Marco. The only thing is that the object is always going to be a little bit in front of the antenna. Okay? But the antenna is following the object. Okay? It is keeping pace with the velocity. However, the object is going to always be a little bit in front. It's not exactly following the speed, but at least the speed isn't increasing. The difference isn't increasing. Okay? Correct. So what does this mean? This means that you expressed it correctly, Marco. This system, if I'm looking at the antenna as this system is the antenna, and I'm trying to make it follow an object, this version of the system is doing its job. This other one, the one we had previously, is not, because it's going further away. So good job, Marco. That was basically it. Luis, you still have your hand up. If you want to add something, please go ahead.
Oh no, it's just that I was actually gonna ask if we have to like how do you say desplazar the graph just above. So the change we need to do just to be like exactly there is kind of easier.
Yeah, in this case, if we're trying to follow the object, that the two lines were exactly on top of the other would only mean that the two objects are moving exactly at the same in the same position. Meaning that if the object is here and you're following it exactly like this. Okay, that's what the two lines together would mean. The fact that there's a parallel separation kind of means this. We're still following the object, but the object is a little bit in front of me, but it's not getting further away, or I'm not getting too far ahead of it. What it means is that I'm tracking it, but it's always going to be a little bit in front of me, okay? But I am tracking it. The previous one doesn't happen that way. In the previous one, we start off okay, but then the object is gonna start getting more separated. Okay, Marianne, go ahead. You also had your hand up. Go ahead.
I have a question. Are we always going to have that little separation? Can we get to a point where the antenna follows exactly the same position as to the
Yes.
object?
Yes, and it has to do with what we were talking about the mathematical model. If in this one, and this is actually what we're going to get to, Marian, it's as simple as that. This one doesn't have an S here on the bottom, right? The other one does. If I put an S, if I don't have, if I put an S here on the bottom, somehow in the transfer function, there's a very easy way to do that. If I put an S there on the bottom, the system is going to have 0 steady state error for a step. That means that for a step, it's going to exactly go to the position, and it's going to have a constant error for the velocity, which is the one we just saw. If I increase the power of the S, then I'm going to have no error in the step. I'm going to have no error in the velocity, and I'm going to have a constant error in the acceleration. And if I keep increasing this S, I'm eliminating the previous types of error. So if somehow I can add an S here to the transfer function, that's how I'm going to eliminate it. So, and that's actually what we're going to get at. If I want a system that has to do with position, and I want it to be really exact with regards to the error, I need to somehow do this. If I want a system that has to do with velocity or acceleration, I need to somehow increase the n of this S. Okay? So yes, it is possible, Mariana. However, the next question you're probably asking and the rest, well, how do I do that? I can do it mathematically because I can just add an S like I did there, but how do I actually do that? Well, actually, the S in a denominator, the S in a denominator here, this has a name mathematically in control theory, and it has a name because it has a mathematical relationship. This here is called an integrator. Any S that I put alone in the denominator is called an integrator. Actually, any S that I put alone in the numerator is called a differentiator. And this literally means an integral, and this literally means a derivative. Now you see what we're going to get at when we have a PID controller, a proportional integral derivative controller. The I part of the controller is this part here that helps out with the steady state error, okay? And physically, an integrator, I can do that many ways. I think you guys are probably already taking, analog electronics this semester. You're going to take it. But remember that you can create an integrator with an operational amplifier and a capacitor. We can create an integral application. But in a PID controller, every letter has a function, and we're going to see that's the next topics we're going to see. Every letter has a function, but the I in a PID directly has to do with the steady state error. By adding a PID controller, I'm automatically adding this S here on the bottom that I need. Okay, so if I have, I don't know how many of you have used PID controllers and had to tune them, but if I'm looking at my system and my system has an error, a steady state error like the ones we're talking about, I need to modify the integral constant. And by modifying the integral constant, I'm going to somehow improve that. I shouldn't move the derivative constant because the derivative constant is for something else. The derivative constant is more used to be able to make the response quicker, and it has more to do with the overshoot and other things. But the I in the integral is going to directly do that. Okay. So I'm getting a bit ahead of myself, but that's where we're going. Okay. Was that
Thank you.
okay, Marian? Marian?
Yes,
Yeah.
it was really fine.
Okay.
Thank you.
Thank you. Okay. Now, that's what we're noticing here with this system. So with this system, we notice that there's an S here on the bottom, and I've gotten a better response to at least a ramp. Now I'm going to, now let's do a parabola, which means the acceleration. And so it's going to be the same system. Now it is going to be to the power of, that's going to be the u, and I'm going to plot it. And notice here that we're still having an error. There's still going to be an error here. Okay, and that error seems to be getting a little bit larger. So we are going to have an error in the acceleration that's going to be increasing. But at least we improved the behavior with regards to the step, which is the constant, and the ramp, which is the velocity. So kind of what we're noticing here is that this S that's in the denominator that we're talking about, because remember one thing, this polynomial here is going to, in the end, have to do with the whole polynomial or characteristic equation of our system. Remember that we had cis G, we had cis G was this transfer function, and the whole transfer function, in the end, there's a part of it that has to do with this polynomial that's transferred over here. Okay, somehow transferred over there. Okay, and so this, remember that this polynomial, the characteristic equation, this is going to define the response of the system. So any modifications I do in that denominator somehow are going to affect the response. And in the end, that's what I want. I want to improve or change the response. So let's talk about that and see how we can get to understanding this a little bit better. We already did it with the graphs. Now let's see how we can mathematically find those values. And these are just the responses that I just showed you. Now, there were a series of mathematical expressions that help us define how the steady state error is going to be. And those are these expressions that we have here. The steady state error given the transfer function, and actually we only need this. We only need this part of the transfer function to be able to talk about the steady state error. And we can find the value of that steady state error using any of these three mathematical expressions or limits. And each of these is going to have a specific limit that's going to be associated to what are called in controlled systems theory, the steady state error constants for position, velocity, and acceleration. Now, how do we get to these expressions? We're going to be using the expressions, but I want you to understand how we get to these expressions. Okay, and I'm gonna walk through that right now. Okay, so first off, there's something that is called the final value theorem. This is math, by the way, and this is, you should have seen this in differential equations, probably. And this is what's called the final value theorem. I'm going to write it down here. What color should I use? I'm going to use orange. So the final value theorem says the following. And I believe this was also referenced to in the videos that I asked you to watch. Does somebody remember what the final value theorem says in mathematically? The final value theorem says that if I have a function, if I want to know the final value of a function, which is basically the limit when t tends to infinite, the limit when t tends to infinite of a certain function, f of t, this is equal to the limit, or this is actually f of infinite, which is the final value of f when f tends to be go towards infinite. Actually, this is the same as having the limit when s tends to be 0 of s times the function in the S domain, or the Laplace transform. And this is what's called the final value theorem. So if I want to find the final value of a function, which means to evaluate the function when time tends to be 0, that is equal to having the function in Laplace and evaluating the function times s when s tends to be 0. And actually, why is this important or relevant? Because it's actually easier to work with this than it is to calculate this. Why? Because of the s equals 0 versus t. S tends to 0 versus the t tends to infinite. So how do we use or we apply this to what we're talking about here with regards to the error of the system? Well, let's remember that the error here in the system, in the transfer function of the system, is going to be this E of S that we have here. The error, let's remember, is the difference between the input and the output. Okay, and the difference between the input and the output is given by the result of this comparison, which is E of S. So E of S, which is the error in the Laplace domain, is equal to R of S minus C of S. We also know that the transfer function C of S, the whole transfer function of the system, is the output divided by the input. And this is equal to, according to the expressions we already know, it's going to be equal to G of S divided by 1 plus G of S. Okay. And from here, we can send this R of S, we can send it over here to this side. And we can substitute this. We can substitute this expression over here. If we do that, we're going to get that E of S is going to be equal to, if we factor R of S, just to make this a little bit more simpler, this is going to be equal to R of S multiplied by 1 minus G of S divided by 1 plus G of S. If I join these two, if I join these two here, or make this into one expression, this is going to be equal to R of S multiplied by 1 plus G of S minus G of S divided by 1 plus G of S. Notice that these two are going to cancel each other out. And in the end, what I'm going to have is 1 divided by 1 plus G of S. So we're going to leave that here. And we're going to have that there. Okay. Now, I know that, or we just said that in the end, what we want is the final value, right? And so let me just do a quick screenshot of this. In a moment, so I can add it. Okay. So what we want in the end is the final value of the error, or the steady state error. So let me just do some quick editing here in a moment. So I can do some copy paste here. Okay. Give me one moment here. Okay. So now that we've got this expression here, and I'm going to write it down, we've got the error, which is E of S, is going to be equal to R of S multiplied by 1 divided by 1 plus G of S. And in the end, what we know is that the final value theorem says that E of infinite, which is the steady state that we're looking for, then is going to be equal to the limit once S tends to be 0 of S times E of S. And so this would be equal then to the limit when S tends to be 0 of S times R of S times 1 divided by 1 plus G of S. Okay. Now, for each of the cases that we've been talking about, for example, Alfredo, go ahead, please.
I think, are you in MATLAB? Because we're seeing the PowerPoint still.
Oh, okay, let me.
Yes, just wanted to say that.
Okay, thank you. Let's see. No, I'm not in MATLAB. No.
No? Okay.
But where was, oh, okay, it got erased then. I'm sorry, I'm gonna go through that again. Just, okay. Now, you can see the screen right now, right? This is the PowerPoint. It's the one that you should be seeing, right?
Yes.
And it's blank right now, okay? So I'm gonna go through that again then because it got erased. Okay, let's go through that again. So again, we've got E of S. So I'm just gonna go through the last part. So the final value theorem is gonna say that E of infinite, which is the steady state error, is gonna be equal to the limit when S tends to be 0 of S times E of S. And we just defined that E of S was the previous expression that we had. So the limit time when S tends to be 0 of S multiplied by R of S multiplied by 1 and 1 plus G of S. Now, for each of the three cases that we had, for the step, the ramp, and the parabola, in the case of, I'm going to do one of them. In the case of the step, R of S equals 1 divided by S. Okay. So if R of S equals 1 divided by S, and I substitute that into the expression, for the case of the step, the steady state error for a step is going to be equal to the limit when S tends to be 0 of S multiplied by 1 divided by S multiplied by 1 divided by 1 plus G of S. What's going to happen in this case to both of the S's? They're going to be eliminated. And what I'm going to be left with is that in this case, I've got a 1 in the 1 here and a 1 plus G of S. In this case, the limit is really just going to be applied to G of S. So this is going to be equal to 1 divided by 1 plus the limit once S tends to be 0 of G of S. which is actually what we had in the previous table that we'd shown. Okay. And that limit that we're talking about there, this limit is called, or has a name. This limit here is called KP, which is the constant, the steady state constant for position. Okay, the steady state constant for position. Now, for the other cases or situations, let's assume that now for a ramp, in the case of a ramp, now in the case of a ramp, R of S now is going to be R1 divided by S squared. Okay, in the case of a ramp. And so what's going to happen now is that I'm going to have the error for a ramp now. For a ramp is now going to be the limit when S tends to be 0 of S multiplied, but now we're going to have an S squared here instead of an S. And so this S is going to be eliminated. The square is going to be eliminated, but I'm still going to have an S in the denominator. That's going to generate for me to have, instead of having a 1 here, now I'm going to have, let me erase this and do that completely. Instead of having a 1 here, I'm going to have, if I multiply that, I'm going to have S the limit when S tends to 0 of S plus S G of S and a 1 here. And so what happens now is if I apply the limit, S is going to be 0, so this would be eliminated. And the limit would only apply to the bottom part here. So what we would have then is that E, this would be equal or equivalent to having 1 divided by the limit when S tends to be 0 of S multiplied by G of S. Okay? This would be the case of the ramp. And so on and so forth. If we apply this to the, if we also apply this to the parabola, we would get similar results. Now, if I go back over here, and this is just to kind of demonstrate what, this is kind of just to demonstrate where this comes from. If we go back over here and look at the mathematical expressions that we have here for each case, we've got the ramp, the parabola, and for each case, we're going to have the expressions like we've been finding, like we've been finding up to this point. We could also do the parabola. We're going to get the same result now that just instead of having an S, we're going to have an S squared. And each of these is going to have a constant associated to it, which is going to be the limit. So this limit is going to be Kp, this limit down here is going to be Kv, and this limit down here is going to be Ka. And they're all going to be with regards to G of S. So the only thing we really need to know of our system is the forward transfer function. Now, what we're going to notice in each of these cases, is that there's going to be a certain behavior of the system depending on the type of system that we have. And that's what was identified as the order of the system that you guys identified. Well, the difference between one and the other one is that it is of a different order. So we're going to classify systems according to their order, but in steady state, we're going to have a specific name for these, and they're going to be called the type of the system. And they're going to be with regards or relationship to the S that's in the denominator of G of S. So what we have is the following, kind of like as a summary. If we have a step input, the steady state error formula is going to be given by 1 plus Kp, where we just have to remember where Kp comes from, which is this expression here that we have here. Okay. And so Kp is going to be a constant. And we're going to have three types of systems, type 0, type 1, and type 2. The type of the system is going to be defined by the S that's in the denominator. So if we have an S in the denominator that's multiplying, if we have no S in the denominator, then that's called a type 0 system because it's S to the 0. Or this is equivalent to having S to the 0. If we have one S in the denominator, that's going to be S to the 1. And if we have an S squared in the denominator, that's going to be an S2 or a type 2 system or an S to the square. So a step input for a type 0 system is going to generate a constant error. Okay. However, for a type 0 system, if we have a ramp, we are going to have an infinite error. And also if we have a parabola, we're also going to have an infinite error. And this is what we saw. If we have a type 0 system like the first one, we're going to be able to react, or it's going to do its job for a constant input, but there's going to be an error. That type of system is not going to be able to do its job for velocity or acceleration. In the case of a type 1 system, we're going to have a 0 error for the step, meaning it's going to go exactly to the value we want for a constant input. It's going to do its job for the ramp, or meaning for a velocity, but it's not going to be able to do the job if we are looking at an acceleration. Lastly, for a type 2 system, we're going to have an exact value of an error. So we're going to go exactly for position and velocity. And it is going to be able to do its job with regards to acceleration, but there's going to be a constant error to that. If we want to continue and have a 0 error, we need to increase the system more. And so a type 3 system, or an S to the 3, would eliminate the error for the parabola as well as the ramp and the step. And that's what we're going to be doing, or that's what we're going to be trying to do, trying to increment the error of the type of the system. Okay.